Fine, okay. Go ahead, Giacomo.
Hi, everybody. Can you hear me okay?
Yeah.
All right. Okay, well, yeah, so for my first presentation today, I'll walk you through this example that we usually refer to as the ghost exchange example. And it is one example that uses MPI and is intended to be a simplified example of what an actual real application code using MPI might look like. So for this presentation, I will give you some background on the specifics of this example. We'll discuss how to compile and run it. And then I'll show you two different implementations of this, one that is using OpenMP and one that is using HIP to offload some of the computations to the GPU. And then for each of these two versions, there are several well, I should say for each of these two implementations, there are several versions that are intended to progressively improve the overall performance of the example. And we'll talk about what each of these does. And then I'll discuss how affinity can further improve the performance of the example without any code changes. Okay, so in this ghost exchange example that I've been talking about, basically we have a rectangular domain that is discretized with a structured Cartesian grid, and there is an initial solution that's defined on a cell-wise fashion. So basically there is one value for each cell. We are using a kernel that we refer to as the blur kernel, where basically this initial distribution of the solution is progressively averaged as the simulation moves forward. So there is this 5-point stencil that's taking information from the present cell and then the 4 neighbors that basically just does an averaging of what the values of these 5 cells are, and then stores it at the center cell, basically. MPI is used in this case to parallelize this process of averaging the solution, where basically the domain is subdivided into subdomains, each of which is assigned to a different MPI rank. And the idea, as you already know, is to have these processes work simultaneously so that basically the problem is decomposed into smaller problems that are solved at the same time. And so parallelism speeds up the simulation. However, because we are, well, in this case, it's a very simplified and simple mathematical operator, but anytime we are using mathematical operators to compute our physical solutions, we use, well, I should say most of the times, the large majority of the times, we are using information from our neighbors. Therefore, since the partitioning of the domain for MPI is done in a non-overlapping fashion, if you are trying to compute the solution at a cell that sits at the boundary of this subdomain, you'll need information from a cell that is owned by a different process. And the idea with MPI is that the memory is not shared, and so a process can only operate on the cells that it owns. Therefore, what happens when we do a parallel run, we have what normally are called the ghost cells. So are cells that belong to a different process that a certain process can read. So for instance, for a given process that owns a cell at the boundary, the ghost cells are the ones that surround the boundary so that that information can be read to advance the solution. But the immediate problem that comes up is that that solution at the ghost cell needs to be correct when we use it to advance the solution. And because it needs to come from a different process, we need to update that. Once it's been computed on the neighboring process, then information needs to be sent to the initial process that is going to use it to advance its solution. And this procedure is called the halo exchange, basically, or the ghost cell exchange. And obviously, these are called ghost cells because they, they don't really belong to the process that owns them. To the process that uses them. And also, they don't exist if you run in serial. For what concerns the boundary condition type, we are using, let's say, outflow type, kind of in a finite volume terminology here, where basically the solution at the boundary is just set equal to the one at the neighboring cell that's at the interior. So this picture here is taken out of Bob's book with Juliana Zamora, Parallel and High Performance Computing. And this is showing the halo exchange procedure considering a domain that's been partitioned among 9 processes. And the halo exchange is done basically with the left and right neighbors first, and then top and bottom. Okay, so as I said, there's 2 implementations of this example, and you can find it in our training examples repo that you have heard so much about already. And the first version I'm gonna discuss is the OpenMP version, where OpenMP is used to offload to the GPU some of the computations. And you can see that the original version is a CPU-only implementation, so there's no offloading to the GPU. And then we have 6 versions and a bonus one that I'll tell you about in a second. So for instance, version 1 is the version where we are using OpenMP to offload to the GPU, and we also use unified shared memory. This is kind of like to mimic what anybody that is running on CPU only might do with OpenMP to port to GPU. So you start by leveraging unified shared memory, or I should say the APU programming model at least. So basically you do not worry about the explicit memory management and try to get something to the GPU quickly, so that you don't get looped into all the explicit memory management, which for somebody that is just starting the process of porting can be rather tedious. Then for version 2, we are adding the RockTX markers for profiling. For version 3, we are doing some modifications using the OpenMP API. So we are allocating the GPU, the communication buffers on the GPU, because initially they were on the CPU, since we started from a CPU-only version. And there's other versions that explore other possible improvements progressively. Let me just skip and go to version 6, which is where we are using explicit memory management. And someone might decide to do that after the whole code's been ported to have more portability, for instance, because a code that's leveraging the APU programming model, yes, will work fine on 300A, but if you need to have that run on discrete GPUs, then it will run if you export HSAXNAC, but it's not going to have the same performance as on 300A. So it makes sense to use, at the end of the porting, some explicit memory management to increase portability and also performance on discrete GPUs in case you run there. And then there's this Orange 8, which is a version that's only on the CPU, but where we have basically split the way the solution is advanced in a way that is asynchronous. So we are first advancing only the cells that do not need information from the halo. Then MPI communication is performed, and then we are advancing the ones that need the halo cells. that we have updated with the MPI communication. So this is a preliminary example that we're gonna port to the GPU in the heap version. So the heap version is the one that I wanted to discuss next. And once again, we have multiple versions here. Most of them kind of mimic what we have already seen with OpenMP. So for instance, for version 3, the communication buffers are located on the GPU using the heap API, so with heap malloc. And therefore, GPU-aware MPI is leveraged, as we have briefly mentioned yesterday. And version 8 for this case is a case where we are overlapping GPU computing with MPI exchanges on the CPU. That's basically the case where we have ported Orange 8 to the GPU using HIP. Okay, so after this quick overview, let's talk about how to run this. So you're gonna have to load the ROCm module, AMD Clang, to have the compilers in your path and set some important environment variables. And then you load MPI here, OpenMPI. And then if you clone a repo, if you haven't already, you just need to navigate into MPI examples, Ghost Exchange, and then Ghost Exchange array assign. And there's also an array assign underscore heap, which is the heap version. So yeah, so to run it after you've compiled with CMake, there's a few input variables that you need to supply. So first of all, notice that we're using MPI run. So -n4 specifies the number of MPI processes. Ghost exchanges are executable. And then -x and -y respectively specify the number of processes that you want to use in each dimension. So in this case, we're running with 4 processes. So we have to make sure that whatever you supply to X times whatever you supply to Y results in the total number of processes that we're using. -I and -j is the number of cells in each direction. -h specifies the width of your halo layer. So since we're just doing a 5-point stencil, we just need the halo layer to be made of one cell, basically. But if you had more complex operators, high order, for instance, then your halo would have to be larger. And you can also play with that. You can make it larger, even though we don't need it to be larger, if you want to increase the communication and see how heavier communication could impact your runtime. So you can play with the -h value, making it bigger, but 1 is the least that we need. And then the -c is whether or not you want to include the corners. Excuse me, it looks like Zoom kicked me out. Can you all please tell me what is the last thing that you heard me talk about?
You were mentioning the -c is the corner.
Okay, perfect. So yeah, so I wasn't cut too much. Yeah, and the next thing in the command is the -I, which is the number of time steps that we wanna run our simulation for. Okay, so in the next couple of slides, we're gonna be comparing how these versions affect the total runtime. So for reference here, we begin with the one that's CPU only, and we are monitoring the time that it takes to advance the solution, to enforce the boundary conditions, and then to do the ghost cell update. And then we also have the total time. And just to give you an example, this is the blur kernel here. So you see we're averaging the solution with this 5-point stencil. XJI is the solution at the current cell, and then the others are all the neighbors in the north, south, west, and east directions, basically. So that kernel, when we are offloading it to the GPU with OpenMP, as you now know, just needs a directive basically outside of the outermost loop, and that will be offloaded to the GPU. For heap, it's a little bit more involved because you're going to have to create your own kernel in heap. And then notice that in this case, since the solution is two-dimensional, we are creating a two-dimensional grid of threads, querying the global ID on each dimension, and then using that to modify our solution. And because we're leveraging unified shared memory, we are exporting HSA_XNAC and setting it to 1. So notice that the total runtime with OpenMP and GPU offload is now 5 times smaller. And with heap is about 2 times smaller. So I should say you shouldn't pay too much attention to these numbers. Take them relatively and not absolutely, because this is not a fully optimized example. You know, it was ran only for a short number of time with only a few processes. So we are not here to show you relevant performance numbers that are absolute. What I want you to focus on is the relative improvements on the OpenMP version specifically, and also on the heap version specifically. Comparing the two of them doesn't really help in this case. Though it's okay to ask and wonder why in this case OpenMP is faster than heap. Yeah, so for comparing version 1 to version 4, version 4 was the one where the MPI buffers were allocated once and for all at the very beginning of the simulation, instead of every time a halo exchange was done. And so there is a bit of an improvement that's kind of the same for OpenMP and heap. You see, this simulation ran for a short period of time, just 5 seconds. So the improvement is not super big, even though it is kind of noticeable. And then we're comparing version 4, which is the one that we just discussed, with version 6, where we are doing the memory management explicitly. So we're not leveraging the unified shared memory anymore. So we can actually unset HSA_XNAC and see that for OpenMP, as you now know, you're going to find a few of these target enter data for the device data management. There's going to be these maps that allocate on the device for the solution, and also for the MPI buffers. For heap, we're gonna make heavy use of heap malloc to allocate on the GPU, and then use GPU aware MPI. So last but not least, a brief mention of affinity, because leveraging affinity and therefore the knowledge of the hardware you're running on can actually give you basically a low-hanging fruit improvement, because you just need to change the way you run your example without changing the code, and you might actually get quite a bit of speed up already. So here you see we are focusing on version 1, and this is just running it without any affinity setting. This is with heap, so you know this is the time that we were getting. And the output here is the IDs of the MPI ranks, the hardware threads each process was running on, and then these are the GPUs that are available to each process. See that they're all available because we have not done any binding, basically. And you see here that there's no binding of the GPU to any process. So there is a script that's available in the repo that's called setGPUDevice.sh. And if you include that as you run your executable, you will see that now there is a binding in place, because you see now the GPU 3 is bound to process 0, GPU 0 is bound to process 3, and so on. And so you see that in this case, you are basically leveraging the proximity of the hardware to minimize unnecessary exchange of data, well, not unnecessary, lengthy exchange of data that otherwise could be faster. As you can see here, basically just including the script gave you a 3.5x speed up. So yeah, so this is it for this presentation. Hopefully it was interesting for you. We like this example because it's kind of like a friendly little code that allows us to show important features actually that you may find out in the wild, and you can somewhat control in this environment that we provide with this example. Yeah, so thank you, and back to the room.
We'll open for questions. Any questions about that example?
Just towards the end, when you did the version with the affinity, taking into account the affinity, could you share that slide again?
Sorry, the audio is breaking up. I can't really hear.
When taking into account the affinity at the end.
Can you show the affinity setting and how it improved the performance? No.
Sorry, you just wanna see the slide, or you would like me to pull the script? Okay.
Yeah, so I just wondered, I just didn't understand what became shorter was the solution advancement, not the boundary condition enforcement.
Right. So what is happening here, and this is a very good question. What is happening is if you go back a slide, all the GPUs are available to each MPI rank. So they're all running on GPU 0.
Ah, okay.
Okay, so, and we've seen this where somebody says, I've parallelized the code, I'm not seeing a performance improvement, but you haven't told it to run on different GPUs. So the next one, we're spreading it across 4 GPUs, and it's surprisingly almost 4x faster.
Okay. Okay. Yeah, I was just confused by those numbers. Okay.
Right, and there's additional steps if you want to pin the MPI ranks closest to the GPU. That's partly in this set GPU device script,
yeah.
But there's a lot of details to set affinity really well on the system. So we aren't doing the affinity talk where we go through MPI, OpenMP threads, how to pin that so that it's best performance, but it can make a big difference.
So I mean, I guess I could look into the script, but this is a very system dependent script, is it? Or
yeah.
Okay.
Although I think this one maybe, can you pop up the code?
Yeah.
So I think this one may be just setting HSA visible devices.
Okay.
Or HIP visible devices. And we have other scripts which will pin the CPU close to the GPU. I don't think this.
Which one were we looking at? GPU device.
So it's really simple.
Okay.
Yeah. Yeah, and there's more complicated ones if you want to dive a little deeper. Is there a question in the chat?
Yeah. Is that because the execution is made on just one MI300A, which made the run faster? I'm a little confused by that question.
Maybe it's the same question I had, actually.
Is it the same? It's, yeah.
Probably.
So the first case, it's all running on the same GPU. Now, there are Slurm settings that you can get it to align the CPU with certain GPUs. I believe you can make that a little bit easier to do with certain Slurm settings. And HPE has some tools to help with that as well, if you got a Cray system.
So what would you have to do to make that HIP version go as fast as the OpenMP? What? You invited that question. What's missing there?
What would you have to do to get the HIP version as fast as the OpenMP version?
Well, I think that probably one way would be to increase the problem size and the number of processes to kind of have a situation that's more realistic and also maybe less prone to unexpected behavior due to everything being smaller. But the real answer is that I don't know. I would need to do some profiling and try to understand better what's the main driver of, you know, the computational time that we're seeing, and then try to see why OpenMP seems to be less affected by that.
Giacomo wrote the HIP version fairly quickly so we have a HIP version to compare. And we haven't looked at why the performance is what we see there.
Is this a common pattern that you is this a common pattern where you try both and then the HIP is slow and you have to optimize it down to get it to OpenMP, or is it?
It's not a bad pattern where you have both an OpenMP and a HIP version and say, why am I not getting the same kind of performance? It's always good to have something to compare against. Yeah. But I think in this case, it was just, I think Giacomo just took a couple hours and wrote the HIP code, so there could be something else going on. This would be a good one to profile to understand why, because there's a lot of asynchronous behavior going on here that it may be different than what you're expecting.
I think there was a question on the chat, or a comment at least.
Yes, slower run shows that the GPUs available are 0 through 7. And this is your question. So if it's available 0 through 7, it's going to pick the first GPU. Yeah. It's not doing what you would assume that it would be running each rank on a different GPU, and that's not necessarily true. And again, this is much easier to understand in a simple example like this than if you have it in your big application and you're wondering, it would be very confusing why the performance isn't what you're expecting. This is a structured grid ghost cell exchange. There are unstructured versions of this, but they're much more complicated code. Performance is even harder to understand for those because there's a load imbalance. Okay, we have 20 minutes here to try that exercise on the MI300A, see if you get the same results. So the example shown here was on an MI210, which is what we had available when we wrote this example up. So you may get different behavior on the 300A. I don't know if you did the last example on the 300A where you were overlapping the CPU communication with the GPU.
I think so. Yeah. And actually, well, I mean, yeah. I wonder because going back to the question about OpenMP and HIP, that initial comparison that we did was leveraging the unified shared memory, but if we do it on 210, then it's not really the same as on 300A. So yeah, as Bob said, you should really test it out now on these machines and see how that changes.
And you can set which GPU you're running on with a script like that, but you can also set it from within your program. So you have a call set device. And there's a different way to do that in both HIP and OpenMP. And so you can do it in your program as well. I think some of the code had commented out how to do it in the code. So we commonly get this question, especially from those who are coming from NVIDIA, what we do to replace the MPS server that NVIDIA uses. And the answer is that our devices, our GPUs are designed to run multiple queues at the same time, hardware queues. So you don't need MPS. You can run anywhere from 4 to 8 MPI ranks per GPU. It will drop in performance at some point, but you don't need a server to do that. When I started doing that trying to use multiple MPI ranks to a GPU on NVIDIA, the performance dropped off drastically. And it may have changed in the newer ones. So it's probably best to get exclusive use of one of the peri-peaks. Run this example.
Yeah, and also let me make the note that when you ask Outlook on AAC6, you also need to specify the number of processes that you want. So the dash lowercase n, and then if you run with 4, you need to have that too.
Yeah, the dash lowercase n is equivalent to the dash CPUs equals a number. There's 192 total for the node. You can request all of them or just use dash exclusive.
So I just ran the 2 examples, by the way, one with HIP and one with OpenMP. And this is the HIP version, 3 seconds. I use the command from the slide, so 4 processes, 3 seconds for HIP, and 2 for OpenMP. So it's already different than what we've seen. Okay, yeah, so let me get to the presentation. Sorry, was getting carried away.